this problem increases as the number of layers increases too. Finally, we are presenting the current state of art that is genetic algorithms, and one of the problems is the high number of iterations and also the different results. In the related works, I'm citing Nagai, okay, he was the first one, okay, Satsuki Nagai. He was working with the CIFAR 100 dataset, and the accuracy increases using genetic algorithms by 12 and 15%. After that, I found another related work related with the pneumonia classification. In this case, it's pneumonia dataset. We have two classes of pneumonia, positive and negative, and the accuracy increases by 2%. Now, as you can see, we are presenting the diagram flow that how the genetic algorithms works. The boxes in orange are the frozen layers of the deep convolutional neural network. As you can see, you can start with n genotypes, okay, 20, 10, 5 genotypes, and randomly you can choose which layers needs to be frozen. And after that, running the genetic algorithms to find and detect the next genotype for the next iteration, you can continue with this process until you obtain the better results. For the experiments, in this case, for the case of study of this article, we were working in the detection of melanoma, okay? So I was working only with two classes. As you can see, this data set was provided by Kagel, okay? And as you can see there, we are considering how many images we are training for the training phase and the validation phase too. And now I'm presenting how it's working the modified binary search and defining what is the maximum number of iterations and evaluations, and using a logarithmic way. And also I'm presenting how many layers has each model that I am working with. In this case, Inception V3 has 311 layers, Inception 132, 427, 769, and 175 for ResNet 50. And the difference with a standard binary search is that we are using a delta in order to add a flexibility in our model. As you can see in the algorithm, is the fourth parameter. Now, for the evaluation of this part, the modified binary search, as you can see in the first iteration, we are evaluating 3 models. It's the same model, but we are not freezing at all in the first iteration, and we have the lower bound score. Sorry, the lower bound index is not freezing at all any layer. Also, we are defining the intermediate bound index, and finally, we are freezing all the layers in order to have the first upper bound. After that, we are going to evaluate the scores, and we are going to detect the next indexes. And finally, we are going to continue the iterations until we have our better value. Now, related with experimental results, we decide to divide the results in 2 parts, the non-overlapped results and the overlapped results. And the word overlapped is defined as if we found an overlapping in the variance of the results for each iteration. In this case, I'm presenting, we're presenting the non-overlapped results as just to add something in this part, you can find the real numbers and results into the paper, okay? In this case, I'm just showing the results. Well, for non-overlapped results, we have an improvement in Inception V3 at 0.28%, just freezing in the first layer. Also, for ResNet 50, we have an improvement of 3%, applying the backward freezing in the layer 66. So if you freeze from the layer 1 to 66, you will have this improvement. And as you can see in the figure, as is shown, our values for the optimal layer score is better than only not freeze at all the layers of the deep convolutional neural network. In the next one, we are showing the overlapped results. In this case, for exception, for example, freezing until layer 6 and using this dataset, okay, remember, it's just only for this dataset. The results may vary if you use another dataset, okay? For exception, we have an increase of 1.45%, applying the backward freezing in layer 6, and DEXNet 121, we have an increase of 0.87% if you apply the backward freezing until the layer 106. Finally, we have a special case, and that is the case of the NAS MobileNet. In the NAS MobileNet, apparently it shouldn't apply this method because internally NASNet Mobile uses recurrent neural networks. So, this kind of neural networks use feedback in its processing. So, the fact to apply the backward freezing in one of these layers can disrupt the feedback, and we have the drop in the score, as you can see in the box plot associated to this slide. At least we noticed that after the fourth evaluation, in the second iteration, the NASNet Mobile was finished because we don't have a better result. And as you can see, if we froze in the intermediate layer, we have a drop in the score. As you can see here, is the best way to work with this kind of network is not freeze at all any layer. Finally, we made a comparison with genetic algorithms, and remember, it's used for this dataset. The results may vary if you use another dataset, but at least we are winning in the categories of average and median, except for DEXNet 121, and we have a technical, well, are very close are the values, okay? Currently, I'm just showing a checkmark table, but in the paper are the numbers, okay? But as you can see, in terms of variance and standard deviation, the genetic algorithm is winning. But the result is very closer. Yes, in 10 at less 4 values is very tiny, so I prefer to evaluate with another dataset. But at least, using this method, you will use less iterations than use the genetic algorithms. For example, if you start with 20 genotypes in order to evaluate this, you at least will have 20 or 40 evaluations in order to detect which layers needs to be frozen. But in our case, it was presented in this slide, at least you will have a maximum number of evaluations presented in that formula. Finally, in our conclusions, and based on these experiments, we can conclude that binary search for transfer learning has a better ROC-EUC score, okay, for inception bit and ResNet 50, and is consistent with the standard and variance in all validation stages. Also, just relying on ImageNet does not guarantee the best score. Also, as was presented in the paper, we can see an overlap despite of the fact we have the improvement in the average, as it was shown here, okay? So we suggest repeat experiments using other datasets. And the use of genetic algorithms can improve the results, but compared with the binary search method for this dataset, remember this dataset, we were able to prove that the binary search has better results because we are using less iterations. And finally, for future works, remember, Nagaes starts this season for the improving the accuracy on pre-trained DCNN, working in genetic algorithms. The work is recent, was presented in September of 2020. So as I am presenting in this slide, the method for selecting layers to improve accuracy in classification tags is relatively new. So for future works, we recommend use or create more methods in order to improve the accuracy on the CNN, in addition to implement genetic algorithms or a modified binary search. Also, we suggest to try with other datasets. And finally, we suggest deep research inside the layers of every DCNN architecture to explain why we are having an improvement, freezing or not freezing some layers. Finally, thank you guys. I really appreciate this conversation with you. I'm ready for any question. And you can access to a simplified code version here. Okay, that's the code, it's in Kaggle. I love Kaggle. And the QR there. Remember, guys, in case you have any question, please let me know. I'm here. The QR. Okay, no worries. Remember, guys, that's was the first draft for my thesis. Currently, for my thesis, I'm working with another dataset and another model of neural network. But at least changing the model, okay, the architecture model for my thesis, we have the same results. We're having the same results.
Harry?
Oh, okay. Will you please repeat your question?
Yeah. Did you use, maybe you missed it, but did you use scientific data for experiments instead? Scientific data.
Scientific data?
Yeah, scientific data.
Like what? Because currently, as you can see, we were working on classification tasks. Classes, as it was presented in this paper. I'm working with 7 classes, and currently I'm working with an undergraduate student in order to improve this method. I don't know if it's possible to show the spreadsheet. I don't know, guys. I have a spreadsheet to present. Yeah, the spreadsheet. Yeah. Please open the first one. Yeah. For example, as you can see in my paper, I was working with 5 types of DCNN. But in this case, I'm working with other types. The selection of the DCNN was in a random way. So in this part, well, the Kaggle URL is there for the experiments. As you can see, applying the iterations and evaluations, we will have some improvements. We will have some improvements in the accuracy. In this case, I'm working with the HAM 10,000, and the HAM 10,000 is a used dataset from the Harvard University in order to classify 7 types of skin lesions. So as you can see, we have an improvement almost of 2% if you use this method. Also, if you open the Inception B3 sheet, yeah, Inception B3 is in the, or Efficient B6, yeah, it's another network, it's not included. Yeah, no, that one. Yeah, as you can see, Inception B6 works with 666 layers. And as you can see, we have an improvement if we apply the backward freezing in the layer 249. It's really interesting because we have ways to improve this algorithm. If you can say the difference between the first intermediate bond, between the first intermediate bond and the upper bond, and the difference between the intermediate bond and the low bond, you can see an approximation. So for some reason, the best result is always running to the left. Also, applying the delta maybe can be improved because maybe we can use a dynamic delta to improve the experiments and reduce the number of iterations. But this is really interesting to explore this part, the optimization of the DCNN. And you can apply also for your experiments using other data sets, not only for image classification. The DCNN is used in many environments. Also, I was reading sometime for signal processing, so you can try with that.
Thank you. So, another question, please. I guess it's okay. Thank you so much. Okay, let's move on to the next presentation.
research scientist at Meta AI. Meta, probably you know, she was former Facebook. Prior to joining Meta AI, she was at Mega Labs, where she led the research efforts on building advanced technologies to enhance search by experience. Prior to joining Megacon Labs, she was a professor of computer science at University of California, Santa Cruz, and spent 2 years at IBM Research Alabama. Her research interests includes data integration and exchange and data provenance and natural language processing. She is a co-recipient of the 2014 ACM Bots Albert Mann Test of the Time Award, the 2018 ICDT Test of the Time Award, and the 2022 Alonzo Church Award. She received the 2019 We Are Living Women in Database Research Award, and she is a fellow of ACM. Welcome back, Chief.
Thank you. So, I'm trying to figure out how to switch to the next slide.
With the arrows, arrow signs. Does it work?
Doesn't work. Yeah. It's on.
Yeah, that is working.
Ah, okay. Thank you so much.
You can point to the one and you can pass me this
Thank you. Thank you so much. Yeah, so thank you for the introduction. I also want to take the opportunity to thank the organizers for inviting me here. I hope I can do more than just delivering this talk. That said, today's topic is on deep data integration, and this is mostly on work I've done before I joined Meta AI, which I joined only last year. If you want to hear about what I'm working at Meta AI, you got to invite me back next year for the talk. And yeah, if you want to translate it to Spanish, make sure you translate this part correctly. So. There are two data integration approaches. One is called the virtual data integration, and the other data warehouse, and today you also know about data lakes. So what is the virtual data integration approach? So in this setting, you have a bunch of data sources sitting on the left here, and there is a global schema that the user sees. So because the user only sees this global schema, she gets the perception that there is only one single data source. Right? When the user poses a query against this global schema, this query gets translated to possibly different queries against the different data sources. The results are obtained from each of these data sources, combined intelligently back to form an answer to the user. So so the user gets the perception that there is only one data source that she's dealing with. So in a data warehouse setting is very similar to what you've seen before, except that you have data actually materialize under the global schema. So when a user poses a query against the global schema, this query is simply executed against the data warehouse, and the results are returned to the user. The data lake setting, data lakes are really, in my opinion, a league of its own. Here you have different data sources as usual. These may be data in different formats. Some may have a schema, some may not have a schema, and they may reside in different places. Still, when the user poses a query, you would like to be able to dynamically discover which are the relevant data sources for answering these queries. You know, grab the relevant information, put them intelligently back together to form an answer to the user. And another distinguishing feature about data lakes is that there are usually a massive number of these data sources that we're dealing with. Okay, so all in all, whether it's a virtual data integration setting, data warehouse setting, or data lake setting, the data integration problem or the data integration ecosystem consists of many sub-problems, right? One is data discovery, discovering which are the data sources that are really relevant for answering the query. After you discover the relevant data sources, you need to understand now what parts of these data sources you actually need to retrieve to get the answer you want, right? And in the process, there's also the schema matching, schema mapping problem. So you need to understand how these different data sources are related or not related to each other, how they're related to the global schema, so that you can formulate answers correctly and return it to the user. And one very prominent problem, which is what I'm going to focus on today, is entity matching. And this is in particular about identifying, trying to understand whether two different entities sitting in two different data sources are referring to the same real-world entity. In addition to that, like I mentioned earlier before, these data sources, chances are that they are not clean. They may have missing records, missing values, or wrong values, or wrong data, wrong formats. All this we have to deal with. So data cleaning is also very much part of the data integration ecosystem. So here's the outline of my talk. What I've done is just to give you like a really quick 5-minute overview of the data integration, data preparation problem. I'm gonna just also quickly go into some of the aspects of deep learning so that we have enough adequate material to do a good study of the entity matching problem with pre-trained language models based on transformers. Right? And then I'll wrap up my talk with some of the challenges and opportunities that I will describe. So actually, also before I forget, a large part of this talk also overlap with some of my past talks. So if you have already heard part of this talk, apologies, yeah, but there's some new material at the end. Okay, so first, what is a neural network? I think most of you here know already, but in case not, let me go through it very quickly, right? Neural network roughly follows the schematic shown here. On the left, you have a bunch of inputs, and the right, usually one output, and in the middle, you have what we call a number of hidden layers, usually at least 2 or more, of neurons interconnected together in all possible ways, right? So this is a zoom-in version on one of the neurons, right? On the left, you get your inputs, the X, and on the right comes an activation function, which is in this case a formula based on 2 weights, W and B, a linear function. Now in standard logic circuits, the output is usually 0 or 1, right? In this case, the output is a linear function, and it has been shown that if the neurons output linear functions, they are more expressive than nonlinear functions. There have been lots of studies on that, why this is so, but this is just to let you know. So what happens in a deep neural network is that you have multiple layers in the middle here, right, of all the neurons with all the activation functions coming out of these neurons. And when we say we are training a neural network, what we are doing is just optimizing what W's and B's should be, right? So that you optimize a certain loss function, right? The loss function, if you optimize that, these W's and B's will converge to some values so that ultimately the entire neural network model will or approximate your training data, the input and expected output very well, right? So that's the general idea. So when we say we train a neural network model, we are really just trying to optimize the W's and B's according to the loss function here. So not surprisingly, there are many ways to connect up all these neurons, and there are lots of architectures out there. If you want, you can take a look at this network zoo. There's a website that tries to curate all these different prominent neural network architectures out there. Right? For example, in visions, people use convolutional neural networks. That's different from what NLP people use. And one particular model that I will try to explain a little bit more about is the transformer-based pre-trained language models. Right? So, you know, in NeurIPS 2017, there was a very famous paper titled "Attention is All You Need" that described the transformer model. And this is built on top of all the different works that exist prior to that, right? All these different neural network models out there. So very quickly, what this paper describes a lot of good properties that transformer models can give you. And in particular, I list only 3 of them here. This is by no means exhaustive, right? So one of the very cool properties of transformers is that they have this self-attention mechanism. What this means is that it gives you a way to compute a contextualized embeddings. And I think these 2 examples here will describe what I mean very well. The first sentence here says, the river bank was covered with flowers. The second sentence says, the bank issued a financial statement. So these 2 words, bank, have totally different meanings, right? Depending on the surrounding words. And that's what these transformers are very good at. It gives you a contextualized embedding of bank so that the embedding here of this sentence of bank is different from the embedding of this bank word in the second sentence. Now, this is a big departure from previous word embeddings like word to vec or glove that exists before that. The ability to give you a contextualized embeddings gives you a more understanding of language, right? So the other cool property it has is multi-head attention. So this means it's able to understand a sentence based on different properties, like subject-verb or subject-adjective relations that exist in a sentence. So it has a deeper understanding of sentences in this sense. Now the third one is a technical trick that they use. Self-attention itself is inherently invariant. They don't care about the order of the tokens, but as we know, in sentences, the order of the words, or the tokens, they are very important. So in that paper, they came out with a neat positional embedding trick that will give the order of the tokens a meaning, of sentences in a meaning in the network. So after that, another paper that came out that defines the pre-trained language models based on transformers is this paper that also started BERT, right, in NACL 2019. The transformers are really these bubbles shown in blue here. You see there are multiple layers, but each transformer is interconnected to the next layer's transformers in all ways, right? So at the bottom, you get your input tokens all sent in simultaneously, and in the top layer, you get all these tokens coming out simultaneously. So I should mention that transformers are not new prior to 2019, so I don't want to give that impression. If you know about models like Elmo, they are also transformer-based. The difference here is that this BERT model, this architecture, gives a very easy way of fine-tuning these models that makes it really popular after that, right? So, and I'll talk about fine-tuning later. This is what we do to fine-tune the model to make it work for the problem of entity matching, which I'm going to talk about, right? So there's a transformers war, right? Ever since, lots of pre-trained language models based on transformer coming out after that. but each one usually targeted for different purposes. For example, the GPT family is targeted as sequence generation, while things like DistilBert, they are deliberately made small so that you have a smaller memory footprint. Right? So there are all this stuff going on. Oops, it's not working again.
It's not based on transformers, I think.
Okay, works now. Cool, thank you. Now we are all experts in transformers. I'm ready to talk about entity matching, which is the real problem I want to talk about, right? So what is entity matching? It's one of the important data integration problems that exist for many years, more than the first paper coming out as early as 1969 by Feligi and Santer, right? So this is like more than 50 years ago. So this is an important problem. Chances are, if you work in any organization with lots of data sets, at some point you will need to do entity matching, right? So what is the entity matching problem? Given two data sources, the goal here is to find all pairs of entities, one from each data source, that refer to the same real-world object, okay? So it can be, the entities can be person, like identifying whether this person Wang Chu here is the same as that person described in that database, Wang Chu, all right? So, like I said, it's one of the most prevalent problems in data integration, and it's important because chances are if you do any data work, you end up doing data entity matching at some point, right? And one of the papers, Gurajada et al. Made an interesting remark that says entity matching, the name itself needs entity matching, entity resolution, because it comes in different forms. It's also known as entity resolution, record linkage, reference reconciliation, duplicate detection, right? Lots of names for it, because it's been around for so long also. Okay, so here's an example of what the entity matching problem is, right? The input here, the input consists of two collections of data entries. It can be relational tables, it can be JSON files, it can be text, right? The system I'm going to describe is agnostic to the format of the input, right? The output is all pairs of entries that refer to the same entity, like person, products, or business, okay? So here I'm showing you two tables, one with 3 columns, one with 2 columns. These are tables about products, right? The goal here is, out of the 9 possible matching pairs, identify which pairs are the right matching pairs, right? 9 because there's 3 by 3, right? So it sounds like a terribly simple problem. So what's the big deal about it, right? Think about it. If you have 1 million records in one table and another million records in another table, and today 1 million records is not a lot at all, right? You end up with 1 trillion records to compare, right? You don't want to end up comparing 1 trillion records because it just doesn't work fast enough, right? So that's one problem. The other problem is how to match. When you're given 2 records, you really have to understand how to make the decision whether these 2 records match or not. So what I've just described is the reason why entity matching is typically divided into 2 stages. One is the blocking stage. It is to try to avoid matching 1 trillion records by applying usually heuristics to just narrow down the set of records to compare, right? This blocking phase, the goal is to have a high recall way of taking out the pairs, right, where precision is less of a concern. But in the matching phase, this is where you really want to know whether these 2 records match or not. So precision is very important here in the second phase. So let's look at this example here. I said there were 9 pairs of records to compare before, right? If I use the heuristic that, you know, for any matching pair of records, they must overlap in one of the word tokens in the title attribute, then immediately I'm reduced 9 pairs to 3 pairs here to compare, right? So, and out of these 3 pairs, only these are the right decisions. these two pairs match, these two pairs don't match, and these two pairs match, right? When we were first studying the state-of-the-art entity matching solutions as far back as April 2020, none of the state-of-the-art entity matching solutions could guess any of these results correctly, right? Could determine any of these results correctly. And when we discovered that, we were studying the data of why they got the things wrong, right? If you see these three pairs of entities, first thing you notice is that there's quite a bit of language involved, right? So language understanding is an important component of entity matching. We cannot ignore that because some data sets are just text heavy, right? The second observation is that the decision, what you think, how you arrive at the decision of what should match or not match is different for different records, right? So in the second example, for example, the title may look very much alike, but actually the addition was very important for making the decision that these two records actually do not match. They are not the same product, right? The same book in this case. In the last case, the model number is very important. In one case, it's sitting nicely in one column. In another case, it's sitting as intermixed as part of the text, right? So you really got to know where to look here. The last example also shows that the data can be dirty. You cannot expect all the data to be nicely structured for you to compare. So you got to be able to handle this messiness in data. Okay, so we thought at that point it would be good to try pre-trained language models to understand how well they perform in the case of entity matching. Because they have already strong baselines for a lot of NLP tasks at that time. That's what we were after. So we fine-tuned a pre-trained language model, and it was cheaper to fine-tune than pre-train it yourself, right? I'll talk more about what fine-tuning means. So this is the architecture of, part of the architecture of Ditto, the entity matching system that we have. So what is shown in the middle in dotted boxes here is just you can think of it as a black box pre-trained language model based on transformers, like BERT, Roberta, or Distilbert in that sense, right? So we pass in tokens, the sequence of records at the bottom, and we attach two layers, the task-specific layers on top, to give us ultimately the match, no match decision. So what fine-tuning means is that you freeze some of the layers, as an earlier talk also mentioned, and adjust the weights and biases of the neurons of the remaining layers, right, using some additional training data. And that's what we did. We got additional training data for match, no match records, pass it through to adjust. In this case, we actually did not freeze any layers, to adjust the weights and biases of all the layers to form a matching model for pairs of records. So to pass in pairs of records, we need to serialize the pairs of records into a sequence of tokens. So what we did was to use special tokens in this case, COL for columns, VAL for values. So column title value is this one, right? Another column manufacturer model number and with the value, another column and value. So we serialize the entire record this way. If you have two records, you just have to serialize twice and add a separator token in between, right? There's always a special token, a CLS token at the beginning, just to signify the beginning of the matching. So now let's take a look at this diagram again. We pass in two pairs of records, and you get these tokens out here as output. What we're focusing on is only this output token CLS here, because this token itself already has a contextualized understanding of both records after it passes through all these layers. And this is the only token we look at to form the match or no match decision, right? As I mentioned earlier, this is a black box to us. We can, in fact, in our experiments, we use Roberta at the time for better performance and Distilbert for smaller footprint, right, for faster training and prediction. We also did a number of optimizations, using like knowledge, external knowledge. One is to inject some common sense understanding into how to identify whether two records match or not, right? So if we know we are matching products, right, chances are model numbers are very important. You can highlight that, right? The way we highlight is to insert special tags in this case, just to surface the fact that this span of tokens is the ID of the product, right? So we do pre-processing of the two tables, in other words, to insert all these tags. And you can, based on the different types of entity, you can do different things. For example, for organizations or employers, you can use the last 4 digits of the phone number as an identifier, heuristic of course, or the street number of the address as an identifier, right? And for products, as I mentioned, you can use product ID or even the configuration, the version number, and so on. So we do injecting domain knowledge, we do span normalization too. Think of phone numbers, there are so many different ways people write and format phone numbers. We just normalize them so that it's easier for the model to know that these are actually 2 phone numbers I'm looking at, right? The third one I think is very important. This is summarization. As you remember in the architecture, I pass in the 2 records to the language model, the pre-trained language model. Now, pre-trained language models have a hard limit on the sequence length. So for the ones we experimented with was 512. Now you can imagine that some records are so long that they don't fit in 512 tokens. So if you don't do anything about it, maybe the second record can get truncated altogether and you're not doing any entity matching, right? So we do have to summarize in this case to make sure that the 2 records fit within the 512 tokens. What we did in our experiments was to use a very simple formulation, just keep tokens with high TF IDF, and that worked really well. But one can also apply more sophisticated summarization techniques from NLP to summarize long passages, for example. The last optimization we did was data augmentation. And this is just a way of getting more training data without having to get it from users and get labelers to do it for us instead, which can be really expensive. Now, for entity matching, there are certain things we can do, which is very important to do also, in addition to getting training data. So one is, for example, we want to tell the model that the order of the attributes do not matter. Right? So for that, we just swap the order of the attributes to get more training data. And by doing so, we are also forcing the model to learn harder on what matters in entity matching, right? In this case, the order of attribute doesn't matter. There is also other operators we use, like dropping a span. Now this is more drastic because by dropping a span of tokens, sometimes you may change the outcome of the entity matching result. And for that, we also have a technique, which I won't talk about here, called mixed DA, which essentially interpolates the original with the augmented record so that the final result gets closer to the original, right? And chances are it won't change the outcome of the entity matching result. So I think I have time for some experiments, right? So we did a couple of experiments to compare our method with the state-of-the-art entity matching solution at the time, based on the benchmarks we can find. So ER Magellan and WDC product matching are the entity matching benchmarks available. We also ran it on the real company data set internally, right? Just to get a sense of how well it does in the real world. So very quickly, the ER Magellan dataset has 13 datasets divided into these 3 domains, and it also has 3 categories: structured, dirty, textual. Structured is like clean data, dirty you have some missing columns, missing values, and textual is text heavy. Some columns are text heavy. The second benchmark, the WDC product matching benchmark, is a bigger data set with more than 200K of product pairs, right? And it's structured into small, medium, large, extra large. Yeah, don't ask me why they name it this way, but it's this way. And the baseline we use is, at the time, the state-of-the-art deep matcher. This was the state-of-the-art deep learning model for entity matching. And what we did was to compare the F1 score and the training time. So I will only show the F1 score here. There's a lot to digest in this table, but I think the key points is that, first of all, Ditto, our system, consistently outperforms deep matcher. Certain highlights are that even for small data sets, like 450 pairs, it was already doing much better than deep matcher. 450 pairs means we have less training data, right? We're dividing like 3-1-1 between training, test, and validation. So these two are the data sets with small number of pairs. The other, I think, interesting thing is for dirty data sets, it was doing much better, right? And if you look at this row, 85% versus 53% was significantly better. Because I will go through this because somehow the pre-trained language models knows how to handle messy data better than other models. The other thing I want to make note is that for text-heavy data, right, it was also doing much better for obvious reasons, because here we are, I think, using language models right from ground up. Okay. So for the WDC dataset, again, this is a lot to digest, but here are the key points. For the small set, right, Ditto's performance is 84%, and that's already much better than here, 79.94% for the medium size, right? Look at the size of the data. Here we have 9,000 records, right, split into 311, right? So the amount of training data Ditto gets is less than the amount of training data Deep Matcher gets, right? And it's still performing better. Okay. I think I'll skip this. The Bayesian study shows that the different optimizations do matter, right? And altogether, they can give important performance. And for the case study with our internal company data set at that time, this was really nice because it really stresses Ditto system. We have 789K of tuples, records in one table, and more than 400,000 entries in another table. So this was a lot in the Cartesian product, and we really have to implement the blocking technique just to run the Ditto part, right? And for that, we have 96.5 F1 score. So this was really promising for matching company records. So this is the overall architecture of Ditto. Just very quickly, there's a blocking phase before Ditto kicks in, right? When you have two tables coming into the blocker, the first thing that the blocker does is to reduce the number of candidate pairs, right, coming out, and before it's passed into Ditto. Now, when you get the candidate pairs, we also downsample and label some of these candidate pairs so that we can fine-tune Ditto for the matcher to work. Within Ditto, there is, like I said, a number of optimization, domain knowledge, summarization, and data augmentation that we do, right? And when you get the match pairs, we can actually also use it to train the blocker in an advanced blocking technique that makes use of deep learning. So I just want to show some related work. There is a lot. This slide is by no means exhaustive. I just want to point out that there was concurrent work at that time. The paper by, where is it? Yeah, Bruno and Stockkinger in EDBT 2020. They had an implementation very similar to Ditto, except that they do not do the optimizations that we do. Okay. Since then, there's also a lot of follow-up work on how to get even better results with pre-trained language models like this. Okay. Also, deep learning techniques have been very useful, not just for entity matching, but for other data integration tasks like information extraction, which involves entity recognition, relation extraction, opinion mining, and table understanding, lots and lots of work in the database community, data curation and preparation, and how to query tables and text together. Right? So, so I want to take a step back now to pop our heads up and see what's going on with applying deep learning techniques to data integration. There are a few reasons, I believe, why it's so successful. One being that deep learning techniques are very suitable for tasks where rules are difficult to specify and features are really hard to engineer. And this is the case for entity matching. You see that we are using, as humans, we are using different rules for different pairs of records to decide whether each pair match or not, right? Also, as you see, some records, language do matter, right? And this is where the strength of all these language models come in. The other thing I think is really important is that language models are very robust to data imperfections, and this constantly occurs in real-world data. You get missing values, wrong values, wrongly formatted values, even if they are correct, right? And sometimes values just don't occur in the places you expect them to be, right? So language models are very good at dealing with missing or wrong values, as the experimental results show. They also have an immense understanding of language, like I pointed out earlier. And there were studies in the NLP community that show that the lower layers of BERT are very good at capturing lexical structure, but the higher you go, you get more semantic understanding of the language. I just want to point you out to the last two rows, bullets here, which will give you a very good understanding of what's going on, right? One phrase that says sharp TV, another phrase that says sharp resolution. The word sharp means totally different things in these two phrases, even though these two phrases overlap, in 50% of the tokens, right? So this is where language models are very good, right? They will say there are different things. Versus the last bullet here, stop hair loss versus prevents thinning hair. These are two phrases that look totally different, but the language model will tell you, like us, that they mean the same thing, right? So that's what they're very good at. So, and attention is key. Knowing what to pay attention to for a different set of records is very important. Like I mentioned earlier, somehow the ability to figure out the addition number is important for deciding that these two records do not match. And perhaps eyeing on the model number here to figure out that these two records do match, right? So what's the catch here? The catch here is that, as you know, right, deep learning models require a lot of training data, and the quality training data is usually really hard to get, right? The slide here is taken from Andrew Ng, right, which shows you, in particular, the difference between traditional machine learning techniques and large neural network models, right? With traditional machine learning techniques, even though you may have a lot of training data to throw at it, at some point the performance plateaus, right? For large neural network models, the more training data you throw at it, chances are you'll get better and better, right? So that's the key here. Another key is that it's not just about throwing more training data, you need to throw more quality training data. And there's an irony here. Sometimes to obtain quality training data, you end up doing a lot of data integration work, data cleaning in particular, just to get the quality training data you need, right? So the disadvantages of using deep learning techniques for data integration, like I mentioned already, is data hungry, and the quality does matter a lot, right? The more quality training data you get, the better it is. There are also fairness and biases. You need to worry about the training data. So think about doing matching between jobs and candidates, right? That's where you want to worry about, how you train your model to match or do not match such important decisions, right? Another disadvantage is that it requires high-performance hardware to execute deep learning models. They tend to be slower and more expensive to deploy. And there are lots of complex, lots of hyperparameters to tune, right? These days you get models with 175 billion parameters. In the older days it was already 100 million to worry about, okay? Now the last one, but not least, is that, as you know also, these deep learning techniques are opaque. And as I've mentioned earlier, if you are using these models to do critical decisions like matching jobs to candidates, you do want to be able to explain why you make a certain decision to match a job to a candidate. And especially the no decision of why you do not match a certain job to a certain candidate, right? So these are very important to, explainability is very important in certain cases. So that said, the challenges and opportunities, I think there is a lot more to be done, right? Because it's data hungry, we can do a lot more in data augmentation to generate additional training data, not just generate additional training data, but know how to, right? So that we are not limited to those data sets. And we need to, a metric for measuring fairness and biases, potential fairness and biases in these data sets. Like I said, model explainability, yeah, so the result, the ability to explain the result of your matching decisions, and especially the ability to explain why you do not match two records. Yeah, so also to take data integration to the next level, right, you want to query heterogeneous data, not just limited to text, right, but also data in different modalities like images, videos today. There are lots of data sitting outside the box today that we need to deal with and also integrate them, okay? So I also want to point out these two quotes from Andrew Ng last year, right? When the system isn't performing well, many teams instinctually try to improve their code, right? But for many practical applications, which is also what we experience with Dito, it's more effective to just focus on improving the data that we have, right? The second one essentially says all things being equal, right? What differentiates a good model from a bad one is really on the data you put in. Okay, so what is next? This is my last slide, right? My question is, can we do data integration for the social good, right? In the world today, we don't just get textual data or structured data. We get a lot more data sitting as images, as videos, as audio, and chances are the combination of all these, okay? Can we integrate data better to understand content better? Now let's take a look at this data sets. It's actually a hateful means data set released by Meta, I think last year or the year before, last year I think. Yeah, so if you look at the text alone, right, of the first picture, let's say, or you look at the picture alone, none of them poses a problem, okay? But if you put the two together, the text with the picture, that's a big problem. It's actually very hateful if you put this, you know, if you post this on someone's timeline or something like that. Love the way you smell today. But you got to have the external knowledge that skunks smell bad, right? Somehow this knowledge needs to come in from externally and integrate with the fact that someone says, love the way you smell today is very sarcastic, all right? So the second and third one essentially says the same thing, right? So the point here being that when you integrate data, you get a better understanding of content, and this is what we need to do next, because a lot of data don't just sit in one modality, but in different modalities and combine, okay? The last bullet, which I'm also very interested in, is whether we can integrate personal data for our own good, to understand ourselves better, right? For example, if I had magically been able to keep automatically what I've eaten or what photos I've taken for the past year or my past entire timeline, right? I will be able to answer the question, what did I eat most frequently in my last 5 visits to San Francisco, right? Things of this sort, to understand yourself better, to know your habits better, to even understand your friends better, because who you interacted with are also part of this timeline, right? Okay, and that's my last slide. I liked before. This is my last slide, right? So this is deep thanks to Yuliang Li, Jinfeng Li, Yoshi Suhara. They were used to be at Megagon Labs, but they're not there anymore, right? And Anhai Duan, who's still at University of Wisconsin. Some of the slides on entity matching are originally from Yuliang, and also Alon Halavi from Meta AI, who gave comments on this talk before. Okay, thank you.
Thank you so much for the presentation, Rosa. Do you have some question, please? Can you hear me? Yeah. Okay. So you have this really nice representation at the base of the transformer, and I guess you could train a two-tower model with the same input, and then use the embeddings at the top of the two towers as input to a nearest neighbor search index, and use that for the blocking technique. Is that what you meant when you were talking about using deep networks for the blocking?
Yeah, so there could be one, but in the one we implemented, it's not using the two-tower model. It was just using the embedding and quickly looking at the KNN, the nearest neighbors, based on the embedding. It was an easy method. There are lots of related work on blocking, and that was not what we were after. But yeah, it was one method of getting the blocking technique, but what you said is another one. I think there was work on that, yeah.
Yeah, thank you very much for the presentation.
In entity matching, well, I have several questions. One of these is, can you match, because one of these strategies is the overlap of tokens or something. Can you relate as well entities that don't match, don't have any overlap of tokens? It can exist, it can be the same entity.
Yeah, so you're referring to the heuristic that I used just to narrow down the number of pairs, right? Yeah, so that was one heuristic. It could be other heuristics, right? What matters in the blocking phase is that it should have high recall. So if you guess that some pairs, or maybe many pairs, do not overlap in one token, then that's a bad heuristic to use, right? So, but in our case, for that example, I know that heuristic will work well, right? So it's a little bit of, heuristics are a little bit of, it's not a foolproof method. It requires you to know your data well in this case, yeah.
And imagine, sorry, okay.
Yeah.
I'm going to monopolize maybe the microphone.
And what happens, here you show several data sets as well. And what is the cost of a false match entity in other domains? For example, biomedical domain. I'm related to biomedical domain, so I know that cost there can be more expensive. It's more critical there than other data sets. Mm-hmm. So how do you evaluate this entity matching, and how you can measure this cost in different domains?
In different domains. It's a really good question and a tough one to answer. But I imagine for medical domain, the first thing is how do you get this labeled data to train your model, right? I imagine that is really, maybe policy-wise, hard to get. And even without that, it's also hard to get labeled data, just, I don't know, which application you have in mind to make the decision. It has to be really high quality. Like if this image X-ray means there is breast cancer, you better know that this is correct, right? So that aside, there is also the cost of deployment, whether you can explain. I think that's another concern I would have if you want to use this for medical domains. Yeah.
Thank you.
Yeah.
Any other questions?
Mark, thank you for the presentation. I would like to ask about the slide when you show the complete pipeline of the D2. Yes, you explain us about the augmented technique. I don't understand really in what cases did you use, for example, augmented technique because you are looking for match data.
Yeah.
So I would like to understand this part of the augmented technique.
So this talk, I was mainly focused on this dotted part of the diagram here, the detour part, which I serialize the data, add domain knowledge, summarize, add augment to train the matcher, right? And when the matcher is ready, the candidate pairs that come in go straight to the matcher, right? And you make a match, no match decision in this case. This table here just shows all the match pairs. Does that answer your question? Yeah.
Yeah, I was asking about the augment.
This one.
Yeah.
Okay.
Yeah.
So
because I understand this library, this component Tito, it's looking to make an efficient match between data.
yeah.
So I would like to understand why we need to use this kind of technique augmented because of this.
Yeah.
Yeah.
So augmentation was
Yes.
a way to get more training data, right? So if I have just like say 500 training data, just by 500 pairs of training data for match, no match. So just by reordering the attribute, I can get a lot more. So from one pair, I can get like maybe 3 or 4 other pairs. To show, when I say ordering of attributes, I really mean, like in this case, I show title, model number, then price, right? I can actually put model number, price, then title as another pair, right? As part of the training data to the system. So you get more training data this way, and that's what data augmentation means. So ordering of attributes is just one way. There are other operators we use as well. Yeah.
But in the case, for example, if you work with structured data, maybe it's not necessary to use augmenting, right?
If you have enough training data, yeah, you don't have to do augmentation. Yeah.
With regard to the computational resources, for example, what kind of server characteristics we need to train this kind of model?
Yeah, so I think we use a couple of GPUs just to run. I don't remember, but this is in a paper. I can dig it up and send it and tell you if you want. Yeah. So yeah, feel free to send me questions. By the way, Dito is on GitHub. It's open source, right? I should have put up the link. If you can't find, let me know. I'll send you.
Perfect.
Yeah.
Thank you so much.
Yeah.
Thank you. Any other question? Si quieren en español, lo podemos traducir. Again, another question.
Yes.
Maybe it's a little bit beyond entity matching. But we were talking about data integration, right? So you are doing entity matching.
But do you have any suggestion or recommendation? What is the kind of structure as well? Because we are talking about integration, data integration. So there is a recommendation of a data structure to start doing this data integration, like common models. In healthcare, it exists common models as well to integrate this kind of data. And talking about the data set that you use in general domain.
Yeah. I think you're touching on a really hard problem. I think coming up with a common model that will accommodate all these different data sources is really hard to begin with, which is why people, I think, abandon virtual data integration. You still have data warehouses today, but it's very instrumented. That's why data lakes are very popular these days. That's what I was going to say. It's really hard to come up with a global schema that, first of all, teams will agree with. That's one thing. And even if you have that global schema, over time, your data sources will change, and you need to update this global schema. So it's painful in that sense, right? And also coming out of this global schema is a non-trivial task itself, right? To be able to represent all these different data sources. In the older days, there was this notion of a universal schema that it's like just take all the columns of all the data sources, put them together, And that's it. That's your global schema. Okay. But yeah, that obviously didn't work out very well too. Yeah.
Right. Thank you. Any other question?
And the last one. Last one. Actually, I was wondering about. It's more technical one, since you use BERT, and you are reducing your text to, applying TF-IDF to extract the most important terms or the most important tokens, keywords. What about, have you ever tried models that take into consideration more tokens, more than 500? Because there are for 1024 and 2048 as well.
Yeah, certainly we can just go for bigger models and hope everything will fit, right? But that was not our purpose. It was good that it was 512 and then we can stress test our summarization technique that way. Yeah. So TF-IDF was, to be honest, it worked well for the data set, but for some other data sets, you may want to use different summarization techniques. Yeah. So.
Well, thank you very much. Let's applaud our students. So let's continue with the presentations. Before our lunch, antes de nuestro almuerzo, vamos a continuar con las presentaciones y tenemos al Leibnitz, Miguel Nunez-Del Prado.
Well, hello everybody. So today, to continue with this presentation, I'm going to talk about profiling public services accessibility based on public transportation infrastructure, which is more an application for data for good. So here the basic idea is to apply what we know on machine learning or artificial intelligence to answer kind of daily based problems. So this is the team. I don't know if, okay. So this is a team from Universidad Andina del Cusco and Universidad Católica. So the outline of my presentation, so first of all, I'm going to give some introduction and try to tell you why this is interesting. Then I wanted to talk about the methodology, show some results, and then make some conclusions. So the basic idea here is to try to evaluate the public services which are essential for citizens and look how far or how close they are from their homes. Because citizens, they need this kind of information, this kind of services to make their lives easier and to perform some things, to have access to health, education, and some other services. The problem is that sometimes we don't have this kind of information in a very accurate way, or even the government, they don't have this kind of information. And I'm going to tell you why. So the idea is to present a metric which is kind of easy to compute, easy to understand for policymakers from the accessibility point of view of the citizen. So our methodology tried to present an index that quantified this kind of accessibility based on distance. So should be very easy to understand. And this time we rely on public transportation system because not all the citizens in a city or in an urban area, they have cars or vehicles to reach this kind of amenities. And we apply our methodology in 2 cities in Peru, one in Cusco and in Lima. So our methodology is in 6 steps. So the first part is to build a transportation network, overlap the public transportation network, then extract all the administrative boundaries, because here we rely on different administrative level 3 authorities, especially in Lima, or municipalities. And then we try to understand, based on this political distribution, the distance to public services for the citizens. Then we compute the index, and then we try to profile the municipalities that are common, that share the same characteristics in terms of accessibility profile. So the first part, I'm going to explain of the graph construction for the transportation network. Basically, we rely on open data, and we build this kind of graph, which the edges represent the streets and nodes represent the intersection of streets. For this, we use OpenStreetMaps to get the infrastructure, and then we get also from OpenStreetMaps all the amenities for different public services. So for financial public services, we have banks. For justice, we have courthouses. Hospitals are for healthcare systems. Marketplaces for food security. Police for justice, and schools and universities for education. Once we have the amenities, we snap these amenities over this graph, and then we get the information from the public institution, which is the Authority of Transportation here in Lima. They have really nice, already useful maps to work with graphs, but that was not the case in Cusco. In Cusco, for instance, the municipality, which is in charge of giving all the public transportation concessions for the roads, they don't have this kind of information in a digital way. So you have just a description of streets. So we did a partner area with the SmartBus company, which is a company from Cusco. They get GPS traces from public services cars, like those ones, to provide geo-target publicity or marketing. So they were very nice. They gave us this information about all the roads that we were able to put into the graph. So at the end of this stage, we have a graph representing the streets of a city and the public transportation system of this city. No? This study is just only in urban areas. I have to clarify that. So once we have that for all the city, we have to intersect this with the administrative boundaries in the cities, because here the political administration in Peru works like that, and many municipalities are responsible for guaranteeing the quality of the infrastructure, so the criticality of the infrastructure. So it's important to know where we have these infrastructure problems, if they exist. So in Lima, we have 43 districts. In El Callao, we have 7, and in Cusco, we have 8. We use GeoPandas and OpenStreetMaps with Network X connection to work all these intersections. So at the end of this part, we have different graphs belonging to different administrative places, where we can perform now our index calculation, which is the distance at the very beginning. So it is very straightforward. So we use the public transportation graph. We have former presented. Over this one, we use just the extra algorithm to give the shortest path and measure the distance. So at the end, we have from every point on the graph, we try to reach different closest amenities. And at the end, we have an origin destination matrix, which is like this one, where you have the nodes in the rows, and in columns you have the different amenities like police station, hospitals, bank, courthouses, schools, universities, marketplaces, etc. So with this OD matrix, we are able to perform the profiling and compute the index for the accessibility. So here the idea was to show in a graphical way the distance that citizens need to go through with the public transportation to reach for instance, a percent of this district coverage with the different services. So for instance, for schools in this district in Cusco, people need to reach like 2 kilometers just to cover 80% of the whole district with this service. No? So we can, in this way, measure how well these, these public services are distributed to citizens. So we perform the same for Lima. So in Lima, we can see that depending on the district, this is just a small sample. You can look all the results on the paper because 50 graphs are not easy to show. And we can see here that in some cases, depending on the district, you need also to go through 10 kilometers to reach different amenities for public services. So based on that, we were able to profile these municipalities. So based on this, we built just a simple heat map where we have the distance here in kilometers, and then we have the public services they covered. So we can see where we have the municipalities that are the critical ones to reach some public services. For instance, here we have this district, which is Poroy in Cusco, is very far away from justice public services, from universities, and in average is the one that has the worst accessibility index for whole the city, no? Which means that in the near future, or the new regional president should invest or make cross-sectoral investments to improve this kind of accessibility for these citizens, no? Because this can also lead to discrimination and other kind of social problems. So we did the same thing for Lima, and we can see that also for instance, for universities, we know in the north, in the south, the accessibility is poor. For justice, no, we have also in the north and the south, and in average, no, we have the districts in the south that do not have very good accessibility to public services. So the problem here is that we have different districts, so many districts in case of Lima, which are 50. So based on all these profiles, we try to build different patterns, so using just a simple k-means algorithm, fine-tuned by a silhouette score. And we try to put together all these districts that share the same, the same pattern of accessibility. So we can see for the cluster, the first cluster, this one, no, we have the distance, no, here the radial, this radial graph, so we have here the distance, and we can see how much they have to go using public transportation to reach different amenities, different public services. And we have, for instance, the cluster 3, which is the worst, because they need to reach a lot of, they need to go through a lot of distance to reach different amenities and public services. So based on this, we were able to profile this kind of districts and give us an idea of the distribution of how good some districts are in terms of accessibility to different public services. So based on this, we can describe different things, no? Like give this methodology for measuring, how good the accessibility is depending on where you live, and we use this kind of index to prove that sometimes we can just do good with public data, with open data, because in some cases this information is very hard to have. So it also depends on the effort of the government to release this kind of information for this kind of analysis. And we also took Cusco and Lima as examples where we found that, for instance, in Lima, we have this information very easy to access and very well structured, which is not the case for other parts in our country. And the idea of this tool is just to provide a way for policymakers to give, the start of discussions for investment, cross-sectoral investments to improve accessibility for people. No? So this is an example of how can we do data for social goods in our country. So if you have any questions, I will be glad to answer. Thank you very much for your attention.
Thank you. Do you have some question, please? I have one question here.
Bueno, primero felicitar por su proyecto, ¿no? Lo que ha presentado. Y mi pregunta, más que todo, era si se estaba considerando las distintas urbanizaciones que se podían encontrar en cada distrito. Es decir, las zonas, digamos, zona comercial, industrial o residencial, y respecto a ello el nivel socioeconómico al cual pertenecería cada persona o dicha población en el lugar que habita, y ya que de acuerdo a ello se podría asociar también el nivel de acceso que tendría hacia los servicios públicos.
Answer in Spanish or? Okay. Gracias por la pregunta. Sí, es muy importante asociar los datos sociodemográficos. Es algo que tenemos pensado hacer en el futuro. La información existe. El INEI provee este tipo de información a través de Redatam, que incluso ya está georreferenciada. El problema es extraerla. Hay que extraerla y trabajarla, pero definitivamente ese es un eje al que vamos, ¿no? De poder justamente dentro de los... acá solo se está hablando a nivel administrativo 3, es decir, municipalidades, pero sí se puede, pues se podría bajar hasta unidades censales para poder justamente ver si hay ese tipo de, digamos, de problemas de que... claro, el problema es de que vas a encontrar definitivamente que las áreas más pobres probablemente tengan una menor accesibilidad frente a otras zonas que son un poco más ricas, por así decirlo, porque van a estar mejor cubiertas por transporte público o por infraestructura vial. Entonces, esa es una dirección a la que vamos. En este caso, incluso, estamos tomando solo la distancia, pero algo que queremos hacer en el futuro es integrar también el problema de la congestión y ver la accesibilidad en términos de tiempo, ya no solo en distancia, y también teniendo en cuenta las características sociodemográficas.
Other question, please?
I don't have really a question, but a comment kind of thing, since we're going to lunch. Did you think about the framework that you have, you can use for something like disaster planning, like earthquake or fire, forest fire?
Yes.
So you have all the infrastructure, all the places. You know where resources lie and how long it takes and all this stuff. And you can plan an evacuation on a quick basis, right? Because when earthquake hits, you don't have time to plan too much. So you need to make an efficient plan for the best side first, meaning that you want that is getting the hard hits right now. It should be said first that you want the thing. And that could be the application.
Yes, thank you for the question. Actually, we use not exactly the same model, but a similar one to plan accessibility for healthcare system in floats and fault line scenarios. The problem is that our approach is very complicated to impute the fragility functions for infrastructure, because the problem when you have this kind of hazards are how resilient is your infrastructure in two ways. The infrastructure you're analyzing, like for instance, schools or, I don't know, hospitals, and then also the infrastructure which are the streets that relay citizens to this kind of services. So We do these kind of things just, for instance, by decreasing speed, because we don't have this visibility of the capacity of the road, the fragility of the road, the maintenance, because there are a lot of variables there that we have to take into account to see the loss function of the infrastructure. But yes, we do this kind of application. Yes, thank you very much.
Another question, please. En español tal vez. Sí, ya funciona, perfecto. En español tal vez, chicos. ¿Alguna pregunta? I guess it's okay. Thank you so much, Miguel, for your presentation.
Lunchtime, and we have to come back in 1 hour and a half, more or less. We start at 2 and 20 minutes, please. 2 hours, 20 minutes.